Welcome to this presentation. I'm going to talk about confidence in machine learning models. And what do I mean by confidence? Well, we mean that the performance measures that we are measuring are accurate. So if we say that a model has an area under the curve of 0.8, it's really 0.8, it's not something else. We also understand things that are a bit more generic, like the model has been sufficiently tested, that the populations are similar to the ones that with the training and testing populations are similar to the ones that for the intended use, and that the model is not using irrelevant data. All these are sort of good things to have for gaining confidence on a machine learning model. Why is this important? Well, the discipline suffers from a lack of rigor. That wouldn't be sort of so bad if it weren't for the fact that we are entering medicine and other life-affecting areas, and then it's very critical to be safe. When lives are at stake, there is no discussion. We also have a governance push these days. You know, your boss, your CTO, even your board may want to know how safe the machine learning methods are. There is a bad publicity effect, which happens all the time. 99 models are good, one is bad. The bad apple spoils the whole thing for everybody. On the more positive side, I think that it's very important to understand, for us as practitioners, to understand how accurate, how much confidence we have in these models. You know, is it really 70% or is really maybe between 60 and 80? That may affect our behavior and how we treat our models. So that's sort of a part of the data that we have about what we are doing. And finally, we need to have a professional responsibility, which in some sense, data scientists and computer scientists are lacking. Engineers have courses in professional ethics. Computer scientists spend their time writing legal disclaimers. That's pathetic. So actually, I wrote this previous slide last week. This week, we had basically a bomb exploding in this area, sort of a sepsis prediction model, which is doing very poorly. If you can, if you can see there, the area under the curve is 0.63. Remember that 0.5 is random. So 0.63 is just barely some signal. This is really a serious issue. Lives are at stake here. And so let me first start by differentiating what we want to do with confidence from the classical performance measures. You know, accuracy, informativeness, precision recall, the F1 that is related to them, the area under the curve, which is a trade-off between the precision and recall. If we have a numerical problem, the L2 norm, many other ways of measuring the performance of the model. That is, how accurately it predicts. And this has a lot to do with the problem itself and with the expectations that we have. For example, if we have a credit card application, this is an example that is in the public domain, we want to determine whether there is fraud or not fraud. Now, that's a decision that has a cost on one side, the bank may lose money, or a cost on the other side, the customer may be really bothered by the fact that the transaction is not allowed. So it's not very simple. And furthermore, 99.9% of the transactions are good transactions. So any method that says yes to each transaction is already 99.9% exact. So this is to illustrate that there are lots of performance measures. We want to select the right one for our application. And the problem that we want to discuss here is once that, for example, we have an accuracy and we know that the accuracy is 95%, we want to know how much confidence we have in this 95%. We're not so much worried about if it's 95 or 90. We are worried about how can we guarantee that this is accurate. So traditionally, we have cross-validation. I'm going to say something more about that. We have two or more levels of testing this is used in some contests like Kaggle and so on, where the testing data is hidden or it's given one at a time, and then maybe finally there is a final level of testing, but this requires in some sense an authority that is looking over you. This also points out to something that many of us mention, that testing once only is a very nice alternative, except that it's completely impracticable. No computer scientist or no data scientist will work and work and work and work, test once, and then if it doesn't work, okay, you have to go home, you have to go to a new project or a new job. That it's a nice idea, it works, and it's statistically correct, but it's not practicable in the world. And negative controls, which is our topic for today, which I'm going to explain later. So why so many? Well, we need as many as possible. The more measures that we have to guarantee the confidence of our models, the better that we are going to be. So another word about cross-validation. Cross-validation is, I don't have the time to explain, it's a method for gaining confidence in your results. Basically test the data with models that have not been trained on that data. But it assumes that the rows are independent, which is often forgotten, which is often not the case. We may have the same patient come in again. We may have all sorts of situations where the data is not really independent. Quite often, it's only computed for a single permutation of rows, and in some cases, it's not even computed at all, which is terrible in some sense. And there is another problem, which is a little bit more subtle, which is the following. You try a model, it doesn't work. You try another model, it doesn't work. You try another model, it works. Oh, and you say, oh, it works at 95%. No, that's not correct. You have tried 3 models and you have picked up the best of 3. And that's not the same statistics as if you had had only 1 and had that result. This actually is part of the reproducibility crisis, a problem that was first spotted in experimental psychology, where they went over 100 papers published in serious journals, and almost 2/3 of them were incorrect. What is the reproducibility crisis? Well, XKCD has explained it very properly with a cartoon. Suppose that somebody says jelly beans cause acne, and so this can be easily disproven. And then you say, oh no, but it's the color that matters. So now you run 20 colors, 20 tests on jelly beans. And of course, one of them is going to pass at the level of 1/20, which is 95%. And so next day in the news, this was jelly beans green, that passed the test. So next day in the news, green jelly beans linked to acne, 95% confidence. Obviously, this is the part of the reproducibility crisis. And what I explained before, that if you try again and again and again, eventually you're going to get the result that you want. It's just that you have to correct the probabilities in that case. So let's get to our topic. Positive and negative controls are something that is completely common in biology and science in general and in chemistry. You are sort of running some test on plates or on vials, and you have data from patients, and then you add a positive control, which is something that you know it has the substance, for example, and a negative control that you know is something that does not have the substance. And suppose that you have yellow means that the test turned out to be positive. And so now we can conclude that yellow, the positive control, the test is working. The negative control did not show the signal, so it means that we did not have any contamination. And one patient A doesn't have the problem, patient C has it, patient B has it at some certain dilution. Typically, the negative controls and the positive controls are all run in parallel, and they are always run. You always want to know whether the test is working, the positive control, and whether you don't have any contamination, the negative control. So how can we export this notion into machine learning? Well, it's quite easy. We can have something that is basically the null hypothesis, doesn't explain anything, and that's typically a column of random numbers, a feature which is produced just with random numbers. If it's produced with random numbers, it should not be able to explain anything. And even better than just choosing random numbers, sometimes it's even better to get some of the features that exist and randomly permute them. Why do this? Because there may be patterns of null information or repeated values that maybe are important to repeat. And so a very good negative control, a very good null hypothesis for us is going to be a feature which is randomly permuted. And so consequently, it cannot explain any of our predictions. And so we get to the first algorithm. The first algorithm is we just introduce a single random feature in our input. We produce a predictor, and we analyze the predictor with feature importance algorithms. Feature importance are algorithms that determine how much each feature affects the result. These are Shapley tests, the Shap values, permutation importance, sensitivity analysis. There are many of them. Actually, there are most of them new to the area, but there are several of them. And obviously, if our random feature shows a lot of feature importance, then that's bad. Our predictor is using a random feature. So the goal is that the feature importance of our random feature is 0, right? It doesn't, when we run this, when we produce this predictor is good enough to eliminate this random feature and not depend on it at all. And if it's not, then it's a red flag that is in front of us. The pros and the cons of this is the following. The costs are very little. It's just one more feature that we have to use in our training that usually very, very easy to tolerate. It does require reliable feature importance algorithms. It is particularly suitable for machine learning methods which add one feature at a time. And in this case, if we have an algorithm that adds one feature at a time, when the best feature to add is a negative control, we know that we should stop the algorithm, that nothing else is worth having. So for that particular case, this is very suitable. On the con side, one negative control is just a binary signal, yes or no, so that may not be sufficient information. And furthermore, when we just try one feature that is sort of a random feature, we may just be unlucky, and unlucky in this case means the random feature happens to be good, and we explain something. So we need to do slightly better. By the way, negative controls are a great improvement over the situation, but maybe we can do even a little bit better. So we go to double-blind tests in medicine. Everybody knows about double-blind tests. Everybody knows about the placebo. Half of the people get the treatment, half of the people get the placebo. This is not exactly what a double-blind test is, but it's what a cartoonist may have thought of it. But for us, a double-blind test is, the double-blind part is not so interesting. What is interesting is that we have two distributions, the placebo and the treatment. And actually the purpose of the double-blind test is to see whether the treatment group has a distribution that differs from the distribution of the control group. The blind part is to guarantee that the numbers don't have biases. But the essence of the treatment is, the essence of the test, is to determine whether the treatment is effective and hence it's different from the control group. Here, we want to do in some sense, the same thing. We have a placebo, which is a random column, and we want to determine whether our features are significantly different from that. So in our second version of the negative controls, we use many randomly shuffled features, but we use them one at a time, and we evaluate them completely. So we evaluate our model completely with each one of the random features. And hence we obtain a distribution of these values, and this distribution of the values is the distribution of the null hypothesis. And now we are able to estimate whether our real features belong to this hypothesis, that is, they are useless, or they are significantly different from the null hypothesis, and then they are good. So this is just an idea to have a sort of a picture about what is happening. The x's here are the values of the negative control. This is a case of a regression. So the error is the sum of the squares of the errors. So larger is bad, smaller is better. So better to the left, worse to the right. And so you can see we have 500 random points in here. They have some distribution. The jagged line over here means the cumulative distribution. The vertical line in the middle is the basis for this problem. So it means that all these points in the right have done worse than just doing nothing, which is not surprising when you give the problem to work with a random distribution, right? A shuffled column. It has no information and is likely to add noise. Just a few of the points are better. And this line on the left is the line that we obtain for the feature that we have selected for that iteration. And hence, what we want to estimate is how far is this point from this distribution? Or in other words, how rare it is to find this point in a random situation. That requires to study the cumulative distribution. And you could, if you have 500 points over here, you already know because the point is, the value is outside all of the points. So the probability is going to be less than 1 over 500, but it's actually even better than that. And that's part of the techniques that we have to use to estimate. The implementation of this it can be implemented for any machine learning algorithm, for which we can also run feature importance. The critical part here, the machine learning algorithm could be completely black box. The feature importance could also be black box, but it has to be a good algorithm for feature importance. As I said before, it works best with algorithms which can be used to select a feature one at a time, and the most promising at every time. The statistics involved, I don't want to scare anybody, but they are not trivial. It's serious statistics that has to go on, in particular to estimate the probability based on the distribution of the points. And in some sense, the good news is that we have produced software pipelines to implement the whole process. But we also recognize that this is an area where people sometimes need occasional help. And so we also offer consulting on this topic. So that's sort of a way of getting a software package is probably something very desirable, but the problem is complicated. And so maybe consulting for many people is the right thing to do.
Can you tell us a little bit about PolyML and what you guys do there?
Yeah, PolyML stands for Polyalgorithm Machine Learning. And originally, we were very interested in trying many algorithms as opposed to the current of, neural networks who do everything and so on. So we are algorithm agnostic, if you want. We have implemented all the algorithms. As time went by, we realized that there was an issue with systems, that it was not just simply algorithms. We are finding that there are lots of problems with the models themselves, and actually with the topic that I just spoke about. So we went into feature importance, and we have put a lot of effort into finding new algorithms and implementing the feature importance and implement it in correct ways and understanding feature importance. And now we are still sort of in the same area. We are finding that people need help when it comes, as this paper that just appeared and showed that the sepsis program is a disaster, that they need to understand what are the measures that they are using, how confident they are they computed properly, are there sort of loopholes in what they have done, are there mistakes on what they have done, sort of lots of things that have to do with good governance of machine learning. And so I think that we are now specializing more in this area of, I would say, of safe machine learning, right? How to guarantee that the machine learning that you wish or that you think you have really is performing so well. I should also say that feature importance is a very critical tool when you have lots of data. The data is expensive for you, and only some of the data is going to be important. And so you don't want to collect all this information all the time. You want to focus on what is important, only get that data, and then do your predictions in the most effective way. So I think that's our space right now, and I think that we have things to offer that are very special for the community, right? We
Outstanding.
have our algorithms. We have our algorithms, but the algorithms, are not what sells the company. I think that these things that are special are what sell.
You mentioned it is important to choose a good algorithm to measure feature importance. Can you recommend one? Is the recommendation agnostic, or some algorithms work better for specific situations?
In general, feature importance should be algorithm agnostic. So I recognize that there are algorithms for feature importance that, for example, look at the neural network or look at the tree and make decisions. Those are really very restricted because they are analyzing the predictor itself. So we look at algorithms that can work with a machine learning predictor that is really a black box, and try to poke that. I would say that permutation importance is a very good one. Sensitivity analysis is a very good one too. We have developed a couple of variations of them. And also Shapley, the original algorithm, is also very good. So that would be my recommendations for feature importance.